Okay, still working in 3 dimensions. We're looking at trigonometry now rather than Pythagoras, but they're clearly all related because it's all to do with measuring triangles, lengths and angles. So, the trick here is the same as with Pythagoras. You try and visualize it or take a section out of the diagram that makes it much easier and look like a 2D diagram. So again, we've got a cuboid with some measurements, and we're going to have to find angles this time. So angle ADB. So find those on the original shape and see what we can do. So angle ADB includes that diagonal and this angle here. It would be super helpful if there was a right angle triangle we could use instead, and we can. The right angle is at A. This is why being a cuboid is helpful. So if we do that, we get something like this, where that is A, that is D, that is B. AD is given, it's 10 meters. AB is given, it's this 20 meters, because all the lengths match on a cuboid. And the angle we're being asked for is this one. So we shall call that theta, or x if you don't like the Greek symbols. And we just need to think back to our right angle triangle stuff in SOHCAHTOA. Compared to this theta, or this theta, that is opposite and this is adjacent. So what links opposite and adjacent? Well, it's tan. So the tan of theta, the tangent of theta, is the opposite over the adjacent, which means that the tan of theta is 20/10, which you could simplify to 2 if you wanted, but it's not required. How do I get theta by itself? Well, remembering inverse functions, we're going to untan, which is arctan or inverse tan. So the theta is the inverse tan of 20/10, or 2 if you've already simplified it. Out comes the calculator. Shift tan fraction 20. I'm just going to type it in as 20/10. And that is roughly 63.4 degrees. Job done. Not too tricky actually, it's just SOHCAHTOA. For a lot of students the hardest part is turning this 3D diagram and getting your head around how it looks to find a nice simple triangle to use. So second example, last example, angle DBH. So where is this angle? How can we use it? Well, DBH takes us from there to there. So we've got this angle. So the right angle's in a peculiar place, so I have to think about how to deal with this. But again, we take out our triangle and draw it if we can. So there's the right angle at D, this is B, this is H, and this is an angle. So we know DH is 6 meters, and that's from the diagram. DB we don't know, and BH we don't know. So we're going to have to work one of those out. We can work that out using some trigonometry. In fact, BD is on this triangle, isn't it? So we can work it out here using some Pythagoras' theorem. So this is going to be the square root of 20 squared plus 10 squared, which is the square root of 500, which will be some nice surd, I reckon. 10 root 5. So that's exactly 10 lots of root 5. I'm not going to get a decimal out here because I don't want to make any rounding errors later. You can type a surd in your calculator fine, so leave it as 10 root 5. So, what have we got? We've got angle theta, we've got the opposite and the adjacent again, which means going to be tan again. I'm going to skip to the end to save you some time. So theta is the inverse tan of opposite, which is 6, over this adjacent, which is 10 root 5s. Your calculator can do the hard work for you. Type that in and away we go. So shift tan fraction 6 over 10 root 5s. Close the bracket, job done, and we get roughly 15.0 degrees to 3 SF. That 0 is functional as a little rounding tip, because if you look at this there are some numbers after it which we have rounded to the 0. So enjoy that. It's not too taxing if you can see how these triangles come from these diagrams. But this visualization is often the trickiest part. This is just SOHCAHTOA. And if this is tricky, you need to go back and revise your earlier material. Enjoy!